Hi, this is another video for SFU Math 310, Ordinary Differential Equations. We are midway through the section on using the Laplace transform to solve differential equations, second order with constant coefficients. And we've seen that one of the primary benefits of this is that we can handle discontinuous forcing functions on the right hand side, the function which we've typically been calling g of t on the right hand side of the differential equation. And we're going to develop a little bit of skill here to handle an impulse function. So what we're thinking of here in sort of physically or possibly electrically is we're thinking of you have some sort of mechanical system, let us say, and that you hit it with a baseball bat. And then you want to see what happens after that. Or you have an electrical, some sort of electrical system, and it gets hit by lightning, or otherwise gets a large impulse voltage applied to it, and then you want to know what's going to happen after that. So we're going to develop the idea of the Dirac delta function in order to be able to handle that kind of force being applied to our system. So we're going to start here, an impulse force, a force of large magnitude applied over a very, or as we'll see, infinitesimally short duration. So we're going to label that g of t. It's an impulse function if it is very large over a small time interval. For some small time interval, we center it somewhere at t naught, and then it will be applied during the interval t naught minus tau up until t naught plus tau for some small value of tau greater than 0, and otherwise it will be 0. So it will look like this. Here we have g of t, and we have t. And we've got the time at which this impulse is centered, and then we've got the time after which it will be 0, and we have the time before which it will be 0, and that it will be that symmetric around the time t naught. Okay, so the force, the function will be large at so this is a large value up here. I'm not specifying yet. I'm not ever going to specify, in fact, what this is, but it will typically be large, and that is what the function looks like. And we can imagine making tau smaller. Okay, so we're going to take a look at a differential equation where we have this type of function that I've drawn here on the right-hand side as the forcing function. Now, an important feature of this type of function and what we want to set it up to have is that when we compute the area under it, so that this integral from minus infinity to infinity of g of t, that is the area under the impulse function, and that is going to be this area right here. So that is right here, area equals to I. And what we want to do is choose the function g of t so that the value of I, the area under the integral, does not change as we change tau. So if I take tau and I maybe make it half the size that it was previously, the area will still remain the same. So in order to do that, we in fact set the function up like this. G of t is 1 over 2 tau if t is between minus tau, and it's 0 otherwise. Let us compute the area under this curve. So I'm going to now take a look at what is the area under this curve. Okay, that area will be the integral from minus infinity to infinity of g of t dt. And that is the area from the integral from minus tau to tau, because g of t is 0 otherwise, so we don't get any contribution to the integral in that case. And then the function is g of t is defined to be 1 over 2 tau when t is between minus tau and tau. And then we're going to integrate with respect to t. Okay, so we need to be very careful that we have the right variable of integration here. It is t. Okay, so this piece here, 1 over 2 tau, that is independent of t, so we can bring that outside of the integral, and we get 1 over 2 tau. And then when we integrate dt, the integral of dt is simply t, and then we're going to evaluate that at the limits of integration, which is minus tau and tau. So we get 1 over 2 tau, tau minus tau. And then that will come out to be equal to 1. That does come out to be equal to 1. Okay, so what is the key point to notice here? That notice I is equal to 1, and it's fixed regardless of the value of tau. Okay, so for that reason we call that the unit impulse function. Now what we're going to do is take a look at what happens when we take the limit as tau goes to 0. So visually, I'm just going to draw a picture of what this looks like. We have some value t naught here that we're going to center the function, and then we start and we have a function that looks like this, and then this value here is minus tau, and this value here is tau, and then this area, the black hash marks here, that area is 1. And then when we reduce tau to say, let us just maybe reduce it to half of what it is, and then we do this, we reduce it, say we reduce tau like this. So now this is tau and this is minus tau. We reduce it, and so we've in this drawing we've kind of halved it. So then in order to keep the area to be 1, I need to double the height. So now I've got a pulse that looks like this. Okay. And the area here is still 1. And I can do that again and again and again, and I can just keep going, sort of thinking about what the limit would be as tau got very, very close to 0. So here's a final version of that. I reduce tau even smaller, and then I get a pulse that looks like this, but that also has area 1. Well, that's the idea. Tau is becoming closer and closer to 0. This function, and that's in quotes for a good reason, is called the unit impulse function, and that's as we take the limit right as tau goes to 0, and we denote it by this symbol here, delta of t, and it's called the Dirac delta function. Okay. It has two important properties. Let me just outline what those are. That is, delta of t is equal to 0 when t is not 0, and the integral from minus infinity to infinity of delta of t dt is 1. Okay. So just as I drew in the graph above, tau is getting smaller and smaller and smaller, the peak is getting higher and higher and higher, and always the area is being kept equal to 1. Okay. I'm using this word function, but really, this is not a function in the normal sense that we use it. It's not actually a function. It's a sort of call this it's a generalized function. So let's just make note of that, so we're not saying anything incorrect here. So delta of t, this is a little point here. Delta of t is not actually a function, although I will use that word. Okay, it's a sort of a generalized function. Sometimes we might see this being called a distribution. Okay, it's it can be put on a rigorous footing, but sadly we're not going to do that here. We just have to accept that we can use it in the manner that we are with it not being really properly a function, but nothing is going to go wrong when we apply our calculus tools to it. This is an important tool. Let me just make note of that. It's an important tool in applied math. And engineering. Okay, the other thing that we're going to note that when I say delta of t, we assume, well, it's not really an assumption actually. It's the unit impulse at t equals 0. Okay, if we apply an instantaneous force at some other time, t equals say t naught, then the corresponding unit impulse is delta of t minus t naught, because that is the unit impulse applied at time t naught. Okay, a key property of the delta function is that the integral of some other function, a continuous function here, f of t, multiplied by the Dirac delta function at time t naught is in fact that same continuous function f of t evaluated at t naught. Let's just make a note. This is where f is a continuous function. Okay, I'm just going to sort of sketch out a bit of a proof and wave my hands around in order to try to convince you of this. Okay, so let us take a look at what this integral looks like. Here it is. It's the limit as tau goes to 0 from the right of the integral from minus infinity to infinity of f of t. And now I'm going to put this back to g tau of t, because I haven't actually taken the limit yet and had this become delta of t. This is going to be delta of t dt. Okay, that is going to be then, as it was before, the limit as tau goes to 0 from the right. Now we only need to really 1 over 2. Well, we know what this function is. That is 1 over 2 tau, and then we're only going to have to integrate between t naught minus tau to t naught plus tau, because g of tau, this function here, that function is 0 outside of the limits of integration, and then at what is left inside here of the integral is f of t, okay, dt. That is this piece here of this integral, these two pieces here, and this piece here has become this, plus it's what allows us to adjust these limits here. Okay, so that's now let's think of what was happening here. As tau goes to 0, we have f of t being approximately f of t naught, really, because we're only sampling the function for a very brief interval time, and the function could be considered to be constant during that small interval. So we're in this interval, t naught minus tau, where we have a where you have the function this original function here is briefly only being sampled at really basically at t naught. Okay, so then we can continue with our integration with that understanding, and we can go like this. Tau goes to 0 from the right, and we're 1 over 2 tau, and now 1 over 2 tau. And we can replace this, here, I'm just going to change my color so we can make it clear what I'm doing. We can take this f of t, and we're going to replace that with f of t naught, which now is independent of t. F of t naught is simply a number. It is a function evaluated at a specific number. So that allows us to move that outside of the integration sign, and then we have here the integral, and what's left? 1 dt, and we still have the same limits of integration, t naught minus tau to t naught plus tau. In fact, it may have been better to see this coming from right here, f of t, one step further along. It's the same idea, but we've already handled the g of tau in the second step. So now we're here, and we can continue, and then we've got the limit as tau goes to 0 from the right over 1 over 2 tau times f of t naught. And we can integrate 1 dt just as we did before, and that's going to be t evaluated at t naught minus tau to t naught plus tau. And indeed, that is f of t naught as claimed. Okay, so that's a basic justification of why this statement is true. Okay, so that's a key feature of the delta function. Now, for what we really want to be able to use this thing for, we want to understand what is the Laplace transform of the Dirac delta function. Okay, so it's not a function, like I said, but the integral above that we just took a look at, this one here, this integral above, makes it possible for us to define the Laplace transform of the Dirac delta function. So the Laplace transform of the Dirac delta function at time t naught, that looks like this. That will be a function, as it always has been, of s. And that, using the definition of the Laplace transform, that is the integral from 0 to infinity of e to the minus st delta of t minus t naught dt. Okay, but we know what this is because we have basically done that up above here. We've got a situation where we've got the Dirac delta function, and then we've got some sort of f of t. In this case, f of t is very special because we're looking at the Laplace transform. It's e to the minus st. So using that integral from above, we can write this as e to the minus s t naught. Okay, so what I'm saying here, this f of t, this is f of t equals e to the minus st when I'm comparing with that integral from above. Okay, so we now know what the Laplace transform of the Dirac delta function at time t naught is. Let me just write that out again. The Laplace transform of the Dirac delta function at time t naught is e to the minus st naught. And according to the Boyce and DiPrima book that we're using, 11th edition, this is formula 17, section 6.2. Okay. So now what we can do is solve any initial value problems that have these impulsive forcing functions. That's our goal here. Let us do one of those right now. This, for one thing, this I'm going to sort of serve as a review as well as of how to solve a constant coefficient second order differential equation with the Laplace transform. I mean, we've done many already where we know how to handle the left-hand side in this case. Now what is new is we have a forcing function that we could not previously handle before, but now we can. On the right hand side, we know what the Laplace transform of that is. So I'm going to go through all of the steps here, but really there's now that we know how to handle that right hand side, there's nothing different from what we've done the previous times we've used the Laplace transform to solve a differential equation. But we will go through this one in detail as a bit of a review as well. So step 1, take the Laplace transform of both sides. Okay, so when we take the Laplace transform on the right hand side, we'll take the Laplace transform of the second derivative. That was going to be, okay, let me just, before I start actually, let me just remind you that y of s is the Laplace transform of y of t. y of t is what we are trying to find. That would be this. That is the solution to our differential equation. So, and capital Y of s is the Laplace transform. So when I take the Laplace transform on the left-hand side of my differential equation, I get s squared y of s. This is now the Laplace transform of the second derivative of my solution. It's s y of 0 minus y prime of 0. Okay, that is this part here is corresponding to the y double prime. Then I move to looking at what the Laplace transform of that is, and that will be plus s y of s minus y of 0. And then I move to looking at what the Laplace transform of this is, and that is going to be 5y of s. Then I take the Laplace transform on the right-hand side. That is going to be the Laplace transform of the Dirac delta function at time 3. Okay, and that's going to be a function of s. Okay, next, so I've taken the Laplace transform on both sides. Next step, apply the initial conditions. Okay, mercifully, in some ways, the initial conditions are the easiest that they could possibly be. Both initial conditions are 0. That will eliminate this term, and this term. Okay, so I'm applying the initial conditions. Then I'm combining all of the terms with y of s and factoring out the coefficients on y of s. Okay, it is not a coincidence that if you were to take the characteristic equation of this thing, we would typically have been using R for that, but the characteristic equation where we were to use, like, say, for example, the method of undetermined coefficients or something like that, we would be solving the homogeneous system, and we would have the characteristic equation R squared plus R plus 5. So that's not a coincidence that it's the same. And then we look on the right-hand side, the Laplace transform of the Dirac delta function applied at time t equals 3. That is e to the minus 3s. Okay, so now we, in fact, in some sense, have a solution. The Laplace transform of the solution that's y of s, and that is going to be equal to, e to the minus 3s over s squared plus s plus 5. And that is e to the minus 3s times h of s. Okay, I am separating it like that because I am seeing that this, when we're going to try to take the inverse Laplace transform, what I am seeing is that we have a formula that allows us to understand that when we delay something in the time domain, we are basically multiplying by this exponential in the frequency domain, or in the domain where we have s as our independent variable. Okay, so I'm going to then be able to use this separation to compute what the inverse Laplace transform of y of s is. Okay, so what I'm saying here, from once I've separated like this, my thought process is that y of t is going to be u3 of t times h of t minus 3. Okay. That is covered this exponential here, and now I'm reduced to finding a inverse Laplace transform of h of s. That the inverse Laplace transform of h of s will be h of t. So I'm here plus s plus 5, and then h of t will be the inverse Laplace transform of h of s. Okay, Now, I have to figure out what the inverse Laplace transform of h of s is. I need to find h of t. Okay, so I guess I'm on step 4 here in some sense. That is, find the inverse Laplace transform. I've sort of gone partway down that road, but I want to finish finding the inverse Laplace transform. Okay, so inverse Laplace transform of 1 over s squared plus s plus 5. Okay, so I'm noticing what I'm thinking. Okay, what am I going to do here? Here's a little bit of a methodical way of thinking about it. Perhaps I take a look at this quadratic. I look at b squared minus 4ac, and I see that that is less than 0. So if the roots are real, then I'm gonna be going for partial fractions. That is not the case here, because b squared minus 4ac is less than 0 for this quadratic. The roots of that quadratic are imaginary, and so I'm in this case here. Otherwise, complete the square. Okay, we've seen both of these tactics before. So let us just write that here. S squared plus s plus 5. I'm now completing the square. I take half of that value there, and I write s plus 1/2 squared. And then I think to myself, if I square that out, I'm going to get s squared plus s plus 1/4. But that's not enough, because I want to see a 5 here, and I only got 1/4. So I have to add the other 19/4. Okay, so you just make sure that the left-hand side equals the right-hand side. Okay, once I've got that written like that, I can see that h of t, which is the inverse Laplace transform, I'll write it in this new form of this thing here, s plus 1/2 squared plus 19 over 4. There. I'm going to now I'm basically being guided by formula 9 in our table, and that is going to be equal to 2 over root 19 e to the minus t over 2 sine square root 19 over 2t. Okay, so that is what is h of t. Okay, then once I have h of t, it's now a very simple matter for me to write out what y of t is. Y of t is u3 of t times 2 over square root of 19, e to the minus t minus 3 over 2 sine of root 19 over 2 t minus 3. Okay, so I just want you to pay particular attention to the fact that this is t, and that's now become t minus 3, and this is t, and this will become t minus 3. That is because we have that this thing here. That y of t is u3 of t, so you see the u3 of t, and then you can see h of t minus 3. I knew what h of t was here, so then here I've put h of t minus 3. Okay, so now I have the complete solution to my differential equation. This is some type of a system, and we imagine at time 3 a large impulse gets applied to it, and then we want to see what happens. And in this case, we have now an expression for what happens at any time t after time t equals 3, because nothing happens until that point. So here we're coming along, and we're right here. So the initial conditions here were 0. We knew that from our initial conditions we had that this is y and this is t. We had that y of 0 was 0 and y prime of 0 was 0. So nothing is happening. Nothing. We're right here at time 0. The derivative is 0. We're coming along like that. Nothing is happening at all. And then and you can see that, in fact, that is this thing here that's causing this 0 to be here. And then at time t equals 3, there's this large magnitude, very short duration, a pulse applied. So that's happening right here. I'll just maybe write that underneath here. So right here, that is when the pulse is being applied. Okay, impulse applied to the system. And then what we can see is the time response of the system after that. And so it sort of immediately responds, and then there's a decaying exponential, and the type of oscillation is sinusoidal. Okay, so we could write this in another way if we liked, without that u3 of t. We could write u of t is equal to 0 for 0 less than or equal to t less than 3, and then afterwards it's equal to 2 root 19 e to the minus t minus 3 sine square root 19 over 2 t minus 3, like that, for t greater than or equal to 3. Okay, so we can get a complete breakdown of what happens after the impulse is applied. So it's the same nice kind of review of how to use the Laplace transform, same as it has been in the last several lectures, but now we can handle some very interesting type of forcing function. That's all for this section. Thank you very much.